Welcome to another session, Data with Nick the Greek. Today we're going to continue our journey of understanding how partitions are calculated when loading data, especially based on Parquet files. And we already saw in the last two episodes how the quite well, not that easy algorithm from Spark is working. And we also did some experiments in the last episode where we saw how maxPartitionBytes, which we're going to be talking today, but also the open cost, the number of cores, the file size, and also the number of files within the Parquet file really influence the partitions when loading the data. So today we're going to talk about maxPartitionBytes, which is one of the configs where you can influence the partition size. So basically, at the end, it influenced the partition split bytes, which we saw in the function before. So it's just one influence factor, depending on the number of cores and the file size. It might also not have any influence, but we're gonna see it later on in the experiment. Basically, what we already evaluate based on the formula. And well, max partition bytes defaults to 128 megabytes. You can use this config with spark.conf.set to set this value. It has to be a string, so you for instance say 100b for bytes. To set it, as I already mentioned, you can influence roughly the limit of one partition size by that. So for experiment, we I generated another data set. So the data set looks as follow. Let's go here a little bit to scroll around. So we have roughly 2 gigabytes of data, and on purpose I took like a non-dividable number of files by 4, so 35 files. So we're gonna have a little bit more distribution within the data sets, as we only have 4 cores in our case. And then in average, we have 60.8 megabytes, or roughly 61 megabytes, which gonna be important. So, and now let's have a look on the experiment setup. If you have questions on the functions I'm showing here, please go back to the previous episode, or the previous 2 episodes. They are really in detail explained how the algorithm Spark is working. Now in this case, we just apply to have some evaluation parameters also to understand what Spark is doing in between. So what are we doing here? So at the end, we're gonna iterate through multiple number of max partition bytes. So here just put it in megabytes. We have our configuration function, which we can quickly just have a look here just to see again how to set up the configurations. Here's the set configs. So it takes a max partition bytes. This is the only one which we want to change. We make a bytes out of it. And then as I mentioned before, we have to make a string out of it and a b so that we can set our max partition bytes. So a lot of functions here. So let's go back to our data set. So for each iteration, we adjust our configurations. Afterwards, we use the algorithm S2 Spark to create our max split bytes. We split the files. We do the file partitioning, and then we do some file partition analysis, which is pretty much calculating the average minimum maximum of each partition size. And then we create here a dictionary just for us to save the data and see the data at the end in a data frame. So, and how it looks like now only for one. So we can see the max partition megabytes, 256, the open costs, the size per core padded, max split bytes, number of partitions, the number of empty partitions, that's what the function did as well, the analysis function, and the minimum, median, and max size. Just to see, okay, do we have deviation of the data there without going to the Spark UI straight away. And I don't want to talk about it significantly more, because let's have a look on the actual results. So what I did is, you're gonna realize in a bit that this was not the most efficient thing I should have done, but I just ran the max partition bytes for 5 to 1024 megabytes. And if you're looking to the results, I saved them for safety purposes into a Parquet file. And the first thing we want to start is, let me uncomment two things here first to really see everything. So if you're looking on all the data and all experiments we did, we should have ordered it. But basically what I want to say, first of all, we have some max partition bytes, which we see here, which are above 1000, above 900. But if you remember correctly, if we scroll up, we have something called the padded max split bytes, the padded size per core. And so what you're gonna realize is once the max partition MB is bigger than 568, let's say, the size per core padded gonna be always the max split bytes, meaning any max partition bytes bigger than this value basically doesn't have any influence. And that's what we saw already in the formula last time. So we basically ignore anything above 570 in this case. So this is the reason that I basically applied this filter. And now that it's gonna be sorted again, let's also have a look on that, if it's really true. So we have our max partitions MB, and okay, I filtered them out. Let's ignore the drop duplicates for now. So, and now we can really see, okay, 567 is bigger. No, 568 is bigger, so it becomes 567.4. 569 is bigger, so it becomes 567.4. So that's basically the first thing what we did. Secondly, what we can see, if we scroll a little bit further up, we can see that especially with the small max partition bytes, we have a lot of empty partitions here. And pretty much it goes down until roughly 62. Let's see, is it 62? Well, 63. And at the end, this makes sense because we saw average size. Of course, we have some deviation of the data set was 60.8 megabyte, meaning we learned that those smaller Parquet files basically are not further splittable. That means based on the algorithm, Spark generates virtually empty partitions. So basically, if we want to choose a good max partition bytes, I personally, for this number of data, number of files which we have, I wouldn't even consider going with this number of bytes. So that means everything above 63 gonna be also filtered out. So now to not have a lot of different max partitions, so we can see that here, for instance, the data distribution doesn't really change. So to really have the partitions where the data distribution changes, I filter out all the duplicates with the same number of partitions, minimum size, median size, max size. So what we end up is now really a smaller data set where we can really analyze what's a good partition size. So what can we see here? So that's the first um, max partition, or that's one of the max partition MB, where we can see even that our algorithm in some cases seems to be a slight deviation, but it's quite accurate. So this is the number of partitions we calculate, and that's the number of the actual partitions. So, and here we see, for instance, we have 30 partitions. So this would be even divisible by 4. So, no, nonsense. It's not divisible by 4. So it's probably not the best partition. And we have here also quite some deviation. So we have quite a lot of small data sets. And then we also have bigger data, bigger partitions in this case. So what we are looking is for like a partition, so in this case 28, which is divided by 4. But also here we see some deviation as before. So also like the data size is a little bit small. Maybe wanted to have a little bit of a bigger size per partition. So let's maybe check if we have some other candidates where the number of partitions is divided by 4. So here we have some 16. What we can see here is we have one. So there you can also see how much difference 1 MB can make in the max partition. So here you see a quite nicely distributed data set. So with 185. But with 186, you can see, okay, here the distribution looks a little bit, is a little bit bigger. So you have here some more smaller files. Also, like here, the next candidate would be 112. Here it looks even a little even better. Therefore, our max size is a little bit bigger of the partition, but this would be also a valuable candidate. Then here it starts with 8. That our partitions become maybe a little bit too big. It depends on how much memory you have. So in my case, as I'm running a lot of things on my computer in parallel, my memory might not be the best, but usually if you don't only do narrow transformations, 8 might be even still acceptable. But you see that you have here especially here quite a distribution from 50 to 300, which might have an influence. And then you only have partitions which are not divided by 4 anymore. So that's basically how you're looking. So for me, the mayor factor is let's have, even if it might not have the biggest performance issue for now, but you're gonna have a lot of follow-up transformations where it might be important to have a good distribution of the partitions, or at least like have a partition number with data, so no empty partitions, which divided by 4. That's like also something you can minimally calculate without low effort. And if you have like not a few files which are very big or very small files, you can actually always find like a good distribution at the end. So now the question is, you see it's a lot of manual work, and can we not even do this somehow automatically? And I thought, okay, let's give it a try if you can do it automatically. And I created here some smaller functions like a partition analyzer. So this is basically just collecting based on a weak paquet partitions function, the partition rows, aggregates it, so basically sums the number of rows we have per partition, and then counts the number of empty partitions, meaning with no rows included, and also calculates the average and the standard deviation. So I thought, okay, maybe we can create some kind of metric if it's like a high distribution or not. And I created here a deviation which is normalized by the standard deviation average. And let's see if this actually works. And so what you can see is basically what the partition analyzer plots out. So the number of partition, and the number of rows after you filter the zeros out. So how is our experimental algorithm looking like? So in this case, I'm going with the max partition 50 to 500. That's where we're iterating. And the first thing we are checking is our number of cores, which is 4. Is this divided by 4? Then we check, do we have zero number of empty partitions? And only then we're gonna check, okay, is our deviation below 0.1? So it's like more something optional. But when I'm going through OLID, we can see basically those are the candidates which it's giving out, which we checked already before. So we have here our 28, we have here our 16. And if you remember correctly, we saw that one had a higher deviation than the other one. So 185 had a quite good deviation. You can also see it here. The 186 had a little bit lower deviation. If you already forgot about it, it's basically those two values here. So you see that this 58 made the deviation a little bit lower here, and you can see it also in the execution time. That this executes a little bit faster, 2 seconds, but well, 2% in this case roughly than the other one. So you can see also that the max partition size has already some effect on the execution time. So that means also like this algorithm shows us, okay, this seems to be a good value to execute. So now let's have a look into the execution time. And I'm just realizing during this video that 185 is indeed one value which I didn't execute. So I execute only 186. So let's do it together right away. And let's have a look into the Spark UI to to see how the different partition sizes behave. So let's see if our 185 execute well. So we have here the 10 megabytes. So right, and then the 10 megabytes. So we come up here in 20 seconds. But if you're going with the 186, or hopefully in a second also 185, we see, okay, here we already have some performance improvement. Also, let's see where our 12 partitions, also here with 196, we can see, okay, it's a little bit, oh, okay, actually, it's a little bit slower here. But we see, for instance, if you're gonna go further up here, so we can see that Sunday, if you're gonna go with 392, which is 7 partitions, you can also like have a bad distribution time. And between the minimum 186 and the maximum, which is 25, it's like 1/3, like 30% performance win, which you can still make. So probably if you have a bigger data set, you're gonna see even a bigger gain. But you see that there is some influence. And let's have a look why we have like this difference. I guess the recording software is consuming here the here my execution time. Okay, there we go. Yeah, that's now 29 seconds because I'm running other things in parallel. But I guess it should have been similar to before. All right, let's compare the worst one with our 16 one, which we wanted now to choose. So we have here the 7 partitions, and we also have quite huge size. And okay, that's quite obvious. So 2 tasks are basically running while all the other cores are not or the other two cores are not doing anything. And as you already know from the previous sessions, that's really important that we use our partitions properly. And here we can also see in the estimation time, some partitions run quite fairly fast, some partitions fairly long. Let's have a look on here on the right in the task. You can also see the number of partitions we have at the end. So let's open our 186 max and B. Even if you saw that there's a little bit more distribution, it seems to have fitted quite well. And the reason might be also that somehow the smaller data sets got compacted in a good way that other cores are not running for long. So and you can see here only one of the three cores is basically running for 2 seconds, and otherwise it's actually quite not too bad distributed. Here we see some deviation, so it's 4 to 6 seconds, and we have only a few partitions which run within 2 seconds. Actually, only one. The majority is running on 4, and then we have here 4 which are running with 6 seconds, which are a little bit bigger. So this might be also the reason that it's running quite well, not too bad. And yeah, that's pretty much it. Looking here. So to sum it up, the max partition megabytes can have performance benefits. It depends on your data. So if you have even bigger data sets, it you might see even bigger deviations. But what to say here is also with bigger data sets, of course, having more workers gonna distribute even bigger. But if you have more workers, more cores, you even have to be even more careful that you set the max partition bytes well. Because you can really, if you set it like too high, you're suddenly gonna end up that you have a lot of executors where nothing is running anymore. So it's the base parameter has a good default value. It also depends on the row groups, which is 128 megabytes, but a little bit adjustments, even a few megabytes already, can really have a significant influence for your performance in narrow transformations, but also for your following transformations and actions you are basically doing. And with that, thanks a lot as always. Um, Subscribe my channel if you like this video. Comment below if you had any questions or comments on that. And see you soon with another episode. Goodbye.